So hello everyone, today we are going to learn how to find the eigenvalues and eigenvectors of a given square matrix. So before going into how to find these eigenvalues and eigenvectors, we have to know what is the meaning of eigenvalues and eigenvectors. So before explaining eigenvalues and eigenvectors, I would like to revise some of the basics of linear algebra. So in linear algebra, we come across a word called vector. So vector, right? And we write this vector as a vector like that, b vector like this. So in general sense, we know that a vector has a magnitude and a direction, right? But in more general way, we can define a vector like this, like a column vector, uh, like a column matrix of some dimension like n cross 1, where we have n number of elements. So it will be a vector of dimension n. So let's say for our example, let's say a is a vector, three-dimensional vector, let's say, and its components are 1 1 1, let's say. So what does this mean? So it means it is a vector in three-dimensional space. Let's say this is our three-dimensional space. Yeah, and this is our x-axis, this is our y-axis, and this is our z-axis. So what is vector A? So you go one unit in x direction, one unit in y direction, and one unit in z direction. You will get a point here in three-dimensional space. Then the vector that will join this origin to this point 1 1 1 will be our vector A. So this is our origin 0 0 and 0. So this vector is our vector A. So this is how a vector is represented as a matrix, as a column matrix in our linear algebra. So now let's look at a two-dimensional example. So let's say we have another vector B, which is equal to 1 and 1. So what does this mean? So it is a vector in two-dimensional space. So let's say we have this coordinate system here, a 2D coordinate system, and let's say this is our x-axis, this is our y-axis. Then this vector will be represented by 1 here and 1 here. So this point will be the 1 1 position, and this vector will be 1 1 vector, and this will be our b vector. This is our origin. Okay. So this is how a vector is represented. Now, how these square matrix are represented in linear algebra. So, what does this square matrix means? How can we interpret them in terms of this kind of graphs? So, let's say we have a matrix. Let's say A equals to let's say 0 1 and let's say it is -1 and 0. Okay, so this is our matrix. Suppose it 2 cross 2 matrix. So what does this mean? So we can call this a linear transformation, or transformation in let call it transformation. So it is a transformation, and so what does this do is it takes a vector and it modified it some way, like it takes a vector and it rotates it or stretches it or compresses it. So let's try to apply this matrix on this vector. Let's say, so if we apply this matrix 0 1 -1 0 on this matrix 1 1, then we'll get 0 into 1 equals 0 plus -1 into 1 is equal to -1, right? Similarly for the second, so this is a 2 cross 2 matrix, this is a 2 cross 1 matrix. So the resultant matrix will be a 2 cross 1 matrix, right? This 2 and 2 will get consumed, so 2 cross 1 matrix. So now 1 into 1 is equal to 1 plus 0 into 1 equal to 0. So this will be -1 0. So we have, if we represent it in the graph, so we'll get this is x-axis, this is the y-axis, Now our initial vector, let's say this is our b vector and this is our b dash vector. So we are getting, and this is our a matrix, a square matrix. So when we are multiplying our a matrix with our b vector, we are getting b dash vector. So it is somehow transforming this b vector into b dash vector. So how is it transforming our b dash vector? That is the question, right? So now let's say this is our b vector 1 1 in x and y. So this is our b vector, and if we draw this b dash vector, then we see it will be minus 1 0. So this will be minus 1 0. In y it is 0. So this is our b dash vector. So what it is doing is it is rotating this vector, and it is kind of compressing it, because its magnitude was root 2, which is greater than 1, but its magnitude is 1. So this operation, this transformation, what it is doing is it is rotating this vector by, let's 90 plus 45, which is equal to 135 degrees in the left direction, or in the anti-clockwise direction, and it is compressing the magnitude of this vector, or this of this vector. So this is what a transformation does in linear algebra. So whenever we see a square matrix, we can think of it like a transformation. So when we apply this square matrix to any space, let's say any vector or any space, it transforms that space or vector. So this is what a square matrix means in linear algebra. Similarly, if we have a 3 cross 3 matrix, then it is some kind of transformation in 3-dimensional space. So if we apply this to any vector, then it will kind of rotate or stretch or compress that vector, right? So yeah, this is the basic idea that I want to introduce before going into eigenvalues and eigenvectors. So as you see, a vector, a matrix, what it does is it transforms a vectors, right? So let's say we have a given matrix A here. So what is its eigenvalues and eigenvectors? So eigenvector of this matrix is such a eigenvectors of this matrix is such a vector that it will not get rotated when it is transformed by this matrix A. So what I mean is, when we apply this matrix A on some vector u, then it will not get rotated. It will be the same vector, but it might get stretched or compressed. So such kind of vectors are called eigenvectors. So these kind of vectors will be the eigenvectors for this matrix A, right? And the amount by which these vectors get stretched or compressed, it will be, the scaling factor will be called eigenvalues. Okay. So we have a matrix A, then we might have a eigenvector which will not be rotated when it is transformed by this matrix A, and the amount by which it is compressed or stretched is called eigenvalue. And there is also a term called determinant of the matrix. Determinant. So what does this mean? So let's say we have a two-dimensional, let's say A is a 2 cross 2 matrix. So what it does is it is a transformation in two-dimensional space. So if we put some two-dimensional space, if we give some two-dimensional space to this matrix A, then it will kind of stretch, or it will kind of rotate that, like it will kind of distort that two-dimensional space. So when this two-dimensional, let's say this is our initial two-dimensional space, and after transforming it with A, let's say this is our final two-dimensional space. Okay, so let's say this is our x, this is our y, then this is our x dash, let's say, and this is our y dash. So let's say this was our like initial area, and then this become our final area. So this was our area A suppose of a cube, let's say, and then this become let's say A dash. So after the transformation, this area, the area, let's say the area that we have sketched becomes traced, or it becomes distorted, right? So this amount of distortion is given by this determinant. The determinant of the, let's say D is the determinant of the matrix A, then the amount of distortion that happened will be given by this determinant. Sorry. So yeah, let's say this is small a because it is the symbols are same. So so A dash will be D A. So the scaling factor of this stretching or compressing of distortion of area will be given by this determinant. So this determinant can also be found out by multiplying all the eigenvalues of this matrix A. So as it is a two-dimensional matrix, so we'll have two eigenvalues. So if we multiply those eigenvalues, then we'll get the determinant of the matrix, right? So this is what the overall picture is. So now let's focus on this, our eigenvalues and eigenvector. So our eigenvector is such a vector that will not get rotated when it will be transformed by a matrix A, and the amount of stretching or compression done by this stretching or compression done by this matrix A will be called this eigenvalue, right? So this is our basic equation. So our basic equation is A u equals to lambda u, right? Now let's solve this problem. Okay, so before going into that problem, we would like to modify this expression somehow. So this is, if we take it to this side, then this will be like this. It will be plus, and then so it was plus, so it will be minus here. Now if we take u common, so this will be A minus lambda I, right? And u is common here. So if A has a eigenvector u which is non-zero, it should not be zero vector, right? So then this term should be zero, right? This expression should be satisfied always. If u is the eigenvector of this matrix and lambda is the eigenvalue for that corresponding eigenvector, then this expression should satisfy. But if u is 0, then there is no meaning of calling it as eigenvector, because null vector is eigenvector for all kind of matrices. So if it is non-zero, then this expression should be equal to 0. That means its determinant should be equal to 0, right? So our first task is to find this expression, and from this we get the values of lambda. Lambda values can be found, okay, from this expression. So let's try to do this first. Okay, then I'll explain the further steps. So our matrix is this thing. So let's copy this thing. Yeah, let's copy this. So we have a matrix A 3 cross 3 matrix. Don't write it. I copied it, so I just paste it. So let's put it somewhere else. Here, let's say. So this is our matrix. So let's write this here, 3 cross 3 matrix, right? So now our first task is to find A minus lambda I. So what is I here? I forgot to mention I is a identity matrix. Okay, identity matrix. So if you are familiar with some kind of matrix manipulation, then you have to put I here, because lambda is a scalar value, right? And A is a 3 cross 3 matrix. So to do this subtraction, we have to introduce identity matrix here. So this identity matrix will again be a 3 cross 3 matrix. So it will look like this. This is 1 0 0 0 1 0, and it is 0 0 1, right? So let's do this operation. Let's try to find out this matrix, because we'll try to find out the determinant then. So our matrix is A is 5 minus 2 0. This is minus 2 6 2, and this is 0 2 7, and minus lambda into our I is 1 0 0 0 1 0 0 0 1, right? Then we can multiply this lambda with this all 1, and then again we'll subtract this. So corresponding element will get subtracted. So it will be 5 minus lambda. This will be remain minus 2. This will 0 minus 2. This will be 6 minus lambda. This will be 2. This will again be 0. This will be 2, and this will be 7 minus lambda. So this is our matrix that we will get after doing this operation. Now our task is to make the determinant of this matrix equals to 0, right? So let's find out the determinant of this matrix. So how to find out? Take the first element of the matrix, 1 1 position element, and then find out the determinant of this small matrix, which you can this 2 cross 2 matrix, and multiply it with the first element. So it will be 6 minus lambda whole into 7 minus lambda minus 2 into 2. So this is our first term. The second term will be minus of minus 2. So when we are doing for the second term, we get minus here to do the to multiply the determinant of this this 2 plus 2 matrix here. So let's do that. So this is a simple procedure that you must have learned in your high school. So let's do this. And the second term is 2 into 0, which will be 0, so I am not writing that. And the third term will be multiplied with 0, so it will not be considered here, right? It will be 0. So let's simplify this. So this is 5 minus lambda, and if we multiply the inside thing, 4 6 are 42, minus 6 lambda minus 7 lambda minus 13 lambda, then minus lambda plus lambda square, this minus 4, and this will be plus 2, and inside it will be minus 14 plus 2 lambda, right? Plus 2 0. Now let's try to do this again, simplify this. So this will be 5 minus lambda, and it will be lambda square minus 13 lambda, and 42 minus 4 is 38 plus 38, I think. Yeah, and now just multiply this, minus 28 plus 4 lambda, right, equals to 0. Now multiply this big thing. So this will be 5 lambda square, 5 multiplied with all these things, minus 13 5s are 65, I think. Yeah, so 5 lambda, minus sign is there. 5 into 38 will be 5 8s are 40, 0 4, 5 3s are 15, 4 190, right? Then multiply minus lambda with everything, so it will be minus lambda cube plus 13 lambda square minus 38 lambda minus 28 plus 4 lambda equals to 0. Now we have one lambda cube term, so it will be here. Let's say lambda square term 1 and 2 here. So 13 plus 5 is 18 lambda square. Now we have lambda term 1, 2 and 3. So this will be let's say add 4 plus 4 is minus 65. It will be minus 61. Minus 61 plus 8 will be minus 69. Minus 69 99. Okay, minus 99 lambda, and 192 minus 28. 190 minus 8 is 182. 182 minus 20 will be 162. So it will be plus 162. I think all terms covered. Now let's go further. Lambda cube minus 18 lambda square plus 99 lambda minus 162 equals to 0. Right. So we got a cubic equation to solve. Now I'll not explain how to solve a cubic equation by hand now. You can use a calculator to find the roots of this cubic equation. Otherwise you can do it by hand. And to know how to do it by hand, please see the next video that I will be uploading. Yeah, I'll give a link below this video to see that video, and you'll learn how to solve a cubic equation. In that video I'll be using this same equation to solve this. So after solving, we'll see that lambda is equal to either 3 or 6 or 9. So we have 3 lambda. Let's say call them lambda 1 is equal to 9, lambda 2 is equal to 6, and lambda 3 is equal to 3, right? Now we got 3 lambda value, right? And our equation is a minus lambda I u equals to 0. So we have 3 different lambda value. So for all these 3 different lambda value, we'll have different eigenvectors. So we have 3 different eigenvalues, so we'll have 3 different eigenvectors also. They might not be different, some might be same. Let's see. So u3. So how to find this eigenvectors? So we have our matrix here. Yeah, so yeah, this is our matrix. Okay, so first we will try to find for lambda 1 is equal to 9. Okay, so if we subtract 9 here in this position, then this is equivalent to a minus lambda 1 I, right? And we'll multiply u and it should be equal to 0. Let's say our u is equal to, we don't know u component of u, it should be a, we already know that it should be a 3 cross 1 vector, and this component, let's say x y z. So x y z, right? And it should be equal to 0. Now if we simplify this, then this will be 5 minus 9 equal to minus 4, minus 2, 0, minus 2, 6 minus 9 is equal to minus 3, and this is 0, this is 0, 2, and this is minus 2, right? And it is x, y, and z equals to 0. Now if we write a different equation, that will come out of this after multiplying this matrix with this matrix. So this will be minus 4x minus 2y, this should be equal to 0. This is one equation. Then minus 2x minus 3y plus 2z, this will be equal to 0. Then this is 2y minus 2z equal to 0. So from this equation we can say that 2y is equal to 2z, and hence y is equal to z, right? So, and from this equation we can say that minus 2y is equal to minus 4x, and yeah, so you can say y equals to minus 2x, right? This 2 will come here. So yeah, we have z in terms of y and x in terms of y. So now what we can do is, we can write our u1 at x, y, and z. So we know x in terms of okay, yeah, so we know our x as x, y as minus 2x, and z as y. So it will be again minus 2x, right? So it will be 1 minus 2 minus 2, and this is x. So u1 is a this vector multiplied by any scalar. This is scalar value, right? X can be any real number. Let x belongs to real number, and this is a vector. So we'll take this as the u1, right? Because this vector and u1 will be parallel, because this is scalar multiple. So this is our first eigenvector corresponding to eigenvalue lambda 1, right? Now let's try to find the same for lambda 2, which is equal to 6. So again do the same thing. Well, yeah, I pasted the matrix. So we'll try to find out uh, yeah this a minus lambda 8 term. So this is a and lambda 8 term, and we'll multiply u2 with this, right? So this is our, let's say x y z, our component of u2. Then this should be equal to 0. Now if we simplify this, then it will be equal to this is minus 1, this is minus 2, this is 0, this is minus 2, this is 0, this is 2, this is 0, 2, 7 minus 6 is 1, right? Let me check whether this recording is going on. Yeah, fine. Otherwise all my effort will be in vain. This is what happened previous time. So I had already recorded this video and I didn't find it. So the recording somehow got stuck in the midway. So after multiplying this, we will get minus x minus 2y equals to 0. Then another equation will get minus 2x plus 2z equals to 0. The third equation will get this will, 0 multiplied x 0, 2y plus z. So this will be called 2y plus z equals to 0. Right. Now from this equation we can say that z is equal to minus 2y. From this equation we can say that z is equal to x, right? So we got x in terms of z and y, yeah, z in terms of x. Let's say from this equation we can get x is equal to minus 2y. So I think we've got everything in terms of y. Let's say from this equation we get x in terms of y. From this equation we got y, z in terms of y. So we can write u2 equals to x, y, and z. So we got x in terms of y. This is minus 2y, y, z is equal to minus 2y, right? So this will be equal to minus 2, 1, minus 2, and y is scalar multiple. This is scalar multiple belongs to R, and this is our eigenvector. We can take this as our eigenvector for lambda is equal to 6, which is our second lambda, right? Now let's move further. Let's try to find out the eigenvector for lambda 3, which is equal to 3, right? So this is our third eigenvalue, for which we are going to find out the eigenvectors, corresponding eigenvector. This is our matrix. So we just subtract this lambda in the diagonal elements and multiply it with x, y, z, and we'll equate it to 0. And if we simplify this, we'll get 2 minus 2 0 minus 2 3 2. This will be 0 2 7 minus 3 equal to 4, and if we multiply x, y, z equals to 0. Now if we get some equation from this, then this will be 2x minus 2y, because we multiply row by column. This is 2x minus 2y, and z term is equal to 0, so it will be equal to 0, and minus 2x plus 3y plus 2z equal to 0. Again third term will be 2y plus 4z equals to 0. So from the third term we can say y is equal to minus 4z, 2y equal to minus 4z, y equal to minus 2z. From this term you can say y is equal to x. So we have our y term. So here we can get u3 equals to x, y, and z. So which term we have expressed? X we have expressed at y. Let's say y we have expressed as z. So y is equal to minus 2z, z is z, and x is equal to y, so it will also be minus 2z. So u3 is equal to minus 2, 1, and this will be equal to z. So this is our third eigenvector corresponding to lambda 3. So if I show the answer to you, yeah, so this is our third eigenvector, this is our second eigenvector, and this is our first eigenvector. First one is 1 minus 2 minus 2, this is minus 2 1 minus 2, and the third one is minus 2 minus 2 1, and our eigenvalues are, so let's write the answer in the last one. So answer, our 3 eigenvalues are 9, 6, 3, and our 3 eigenvectors are u1, u2, u3, and you can see above what are u1, u2, u3. I have to write, I have TP. Okay, so thank you for thank you for your patience, and yeah, have a good day.